So our next speaker is Rob Myers, and he will tell us about holographic scattering and non-minimal RT surfaces.
So we're not quite set up, so I just wanted to thank the organizers for bringing us all together in this marvelous environment for a wonderful workshop, and it's a real pleasure for me to be here. I haven't been here for, well, since this was a construction site, I guess. In any event, well, we heard the title there. This is about a recent paper that I wrote with some very smart people. So Jackie and Batya are still PhD students in Waterloo. Alex is one of the junior faculty at Perimeter, and Olga's now moved on to bigger and better things. She's with the CRNS in Paris. So I'm going to start with my favorite slide of all time, holographic entanglement entropy. And so this is just a quick reminder. I know you've all been, or most of you have been at the school, but the idea is in ADS-CFT, we've got a boundary conformal field theory. We're going to set up an entanglement entropy problem. So we're going to look at a particular region on a time slice. We're going to integrate out the degrees of freedom in the complementary region. That leaves us with this density matrix. And then to measure the correlations or the quantum entanglement between the degrees of freedom here and in the complement, we evaluate the von Neumann entropy, or alternatively the entanglement entropy of that density matrix with the usual formula. Now that can be a difficult or a challenging problem in even a simple free field theory. And here we have conformal field theories with strong interactions and large numbers of degrees of freedom. But what our friends Takayanagi, Aru and Takayanagi taught us is that holography lets us translate this difficult calculation in the boundary conformal field theory into a simple or relatively simple geometric formula in the dual gravity theory. And so what we're doing is we're considering all surfaces hanging down in the bulk that are homologous to my region A. On those surfaces, I evaluate the Bekenstein-Hawking entropy and I extremize. And the result is then the desired entanglement entropy for this boundary region. Now, that turned out to be a very useful formula or an arena for discussions about ADS-CFT, and I say that it formed, or it led to a fruitful dialogue between the bulk and the boundary, in that we learned new lessons, using this idea, we learned new lessons about quantum field theories, in particular strongly coupled quantum field theories, but in the bottom here, we also learn new lessons about the nature of quantum gravity. There's one technical point that I wanted to remind you about, and that is that in certain cases, we may find more than one extremal surface, and in that situation, we're instructed to choose the one with minimal area. And so a simple example where that arises and which is going to play a role in today's talk is if I'm looking at my boundary and my boundary region actually has two disjoint pieces. Then we can have two possibilities. There may be what's called the disconnected phase where the Ryu-Takayanagi surface is just the usual Ryu-Takayanagi surface that I would have evaluated for each of these regions individually, or there may be a connected phase where the RT surfaces actually stretch between the endpoints or the boundaries of our two regions to form a single connected entanglement wedge in the bulk. Now, what distinguishes these, or a measure that distinguishes these two, is the mutual information, which gives us a measure of the correlations between these two regions, and it's given by this formula here. I'm evaluating the entanglement entropy of A and B, and then subtracting the entanglement entropy of the union. And if I evaluate that formula in the first case, I'm just going to get 0 according to the formula I've given you. But what that means is that the mutual information is a quantity that's of order 1. It's going to be given by quantum corrections to this classical geometric formula. On the other hand, in the case of the connected phase, the entanglement entropy here, or the mutual information rather, is large. I mean, there are a large number of correlations or entanglement between the degrees of freedom on the two sides of the boundary. So that's my lightning review of entanglement entropy, holographic entanglement entropy, and I've put an outline here just to give you an idea of where I'm going, because there are many different steps. And so next I'm going to be talking about, or I'm going to introduce the idea of holographic scattering and the so-called connected wedge theorem. I'm then going to take a look at some very specific examples where I'm going to apply these ideas. In three-dimensional ADS, we're going to look at conical defects. We'll take a flash view at the same results for BTZ black holes. And then I'll try and interpret the results that we find here, and then I'll just wrap up with conclusions and outlook. So on to holographic scattering. Here, this is really an idea that was developed and pioneered by Alex, but he's had various collaborators in developing those ideas. But I'm going to think about, first of all, a two-dimensional boundary, and so that's what I've drawn here. And so there's a three-dimensional bulk, and what that means is when I'm talking about Ryu-Takayanagi surfaces or holographic entanglement entropy, my extremal surfaces are actually just geodesics between two different points on the boundary. Now, in the case of the holographic scattering, what I'm thinking is that I have two inputs at the boundary or at the bottom of my picture here, and then I've got two outputs that I've positioned at a much later time. Now, these are all put on the same time slice, and that's just for the convenience of drawing. But I'm going to ask the question, okay, before I ask the question, I'm going to describe what these decision regions are. What that means is if there's an input here at C2, it can decide to go either to R2 or R1, but I can't wait too long. As long as I'm an observer that enters at this point, I can make a decision anywhere in this green region to head off to R2 or to R1. And so that's why it's called the decision region. Technically, what I've got is I'm looking at the causal future of my input point and the causal past of the two output points and looking at the intersection of those. And one of the things you'll notice about the notation here is they all have hats on them. And hats in my notation means that's something that I'm describing on the boundary. When I drop the hats, I'm talking about something in the bulk space-time. This whole picture, yeah, that's the boundary, so time runs up. In principle, it's infinite in length. I've just got an initial time slice and a final time slice. And then this is the phi direction, that's angular. That's an angular direction, and so I identify the two sides of my rectangle to make a cylinder. Now, having described the decision regions, the mission or the task that we're going to consider is imagine that I have a message that I'm inputting here at C1, but given a signal at C2, I want to send that message either to R1 or to R2. And so in this particular situation, there's no obvious way to do that. However, there are other configurations, in particular ones where this decision regions overlap. That requires then that I move my points, my output points around a little bit. But in a situation like that where I've got an overlap, clearly what I can do is I can take my message over to this region over here. I can take my signal to the same place, and then comparing them, I decide either I send the message to R1 up here or to R2 over here. And so clearly there are configurations where that task is obviously possible. However, what that relies on is that there's an overlap of all four of these causal regions, in particular the causal futures of the two inputs and the causal past of the two outputs up here. However, if I go back to the original picture, I don't have an overlap like that, and I would say that this scattering region, the overlap of all of those causal regions, is the empty set. However, it still may be possible in the context of a holographic system where I've got a strongly coupled conformal field theory in play, that I can still carry out this task. And that's coming by sending the message through, a dual version of the message and the signal through the bulk to some common point in the middle of the space, and then from there deciding whether it goes to R1 or to R2. And so in that case, what I need is that this scattering region, which again involves the causal futures of the inputs and the causal past of the outputs, to be non-vanishing. But note again that here I've dropped the hats, and so what I'm talking about now is a scattering region that lives in the bulk, not in the boundary. What's interesting here is that the scattering region on the boundary is vanishing. There is no scattering region, but there's a non-vanishing scattering region in the bulk. What Alex noted, though, was that in the case where that scattering region in the bulk is non-vanishing, then the entanglement region associated with these two decision regions is in fact in the connected phase, i.e. there are a lot of hidden correlations, or there's a lot of quantum entanglement between those two regions. And that entanglement then serves as a resource to facilitate this scattering in the bulk. And so Alex has gone on to talk about this in the terms of non-local computation in the boundary theory, but the key idea is that I have these two inputs, but those inputs share a lot of, there's a lot of entanglement in the decision regions, as I said, and that serves as a resource to produce or to carry out the task. And in fact, with his collaborators, Jonathan Source and Benny Yoshida, he developed what's now called the connected wedge theorem. Essentially, it's the same idea that I described with a few technical changes. One is that instead of talking about input and output points, they're talking about regions. And so when I talk about the corresponding bulk regions, I'm talking about an entanglement wedge rather than the causal future of a point, say here. The other thing is that it's a quite, before I was drawing pictures just for ADS3, now we're talking about asymptotically ADS3, and so I can imagine that my geometry contains excitations, scalar fields or photons propagating about, or even black holes. But the key idea is that we define these decision regions in the boundary using the causal future of my two input regions and the past of my output regions, and I look for a scattering region in the bulk, which corresponds to this particular intersection. And when there is a scattering region in the bulk, what their theorem shows is that the entanglement region of these two, or the entanglement wedge of those two, is in fact connected. But one of the things we note is that the theorem goes one way. If I have a scattering region, I have entanglement, but entanglement by itself here does not imply that there will be a scattering region. And so that's actually the part of the theorem that we're going to examine by looking at some simple examples more carefully. So again, we're working with a three-dimensional bulk, and one of the simplest solutions that we know is the BTZ black hole, and so it's a metric given here, and my pictures or my cartoon conformal diagram looks something like that, where I've got a black hole in the middle or an event horizon. In this particular case, I'm working with the parameter m, the mass parameter being positive, but there's also another set of geometries described by the same metric, which is the conical defect. And here I'm allowing m to take negative values between 0 and -1. Of course, if m is -1, i.e. I have a +1 here and here, this is just empty ADS space. When I'm in this regime here, I'm cutting out a wedge and gluing it together, and I have a conical defect at the center of the space. For most of the discussion, I'm not going to be drawing these pictures. Rather, I'm going to be drawing time slices through my spaces. And so here, for the conical defect, I'm just going to stick a dot indicating a defect at the middle. In this case here, my black blob indicates that there's an event horizon for the BTZ black hole. And that's a good question, and there is no theorem in higher dimensions. And if you ask me again, that's an outlook question. I was going to say that these pictures are enough because in what I'm looking at, I'm going to spend a lot of time looking at RT surfaces, and they're just going to live in fixed time slices in the bulk. So I want to set up a particular problem to look at. And so here I've got my two input regions, and to make life simple, I'm setting it up in a very particular way where the two input regions have the same size, called X, and they're separated by the centers of those two regions are centered by an angle theta. And clearly there are some restrictions here. X should be less than theta, otherwise these two regions are going to be overlapping. In that case, it's not a mystery. I can do the scattering process in the boundary. And so I'm interested in these cases where it's not obvious that the scattering occurs, or it can only occur through the bulk. And I've put a restriction here on theta because if I go beyond theta equals pi, then I can simply reflect the diagram around. And instead of theta, I can think that the new angle that plays that role is pi minus theta. Yep.
In your setup, you focus on basically the case that the boundary is living on a cylinder.
Yep.
And you related this to the phase transition that corresponds to RT surfaces snapping.
Yep.
But how about the Poincare case? Like if your boundary is like just planar, you still have the RT phase transition. But how does the scattering work in that case? Is there scattering?
No, you can set up the same problem. If you wait one slide, I can just say, make this infinite, and that would be the case that we would study. So here's our setup. As Nima was pointing out, I've got a cylindrical configuration, so I'm identifying these two sides. I've got the decision regions or the input regions, which had a width x and a separation theta. I've chosen the output regions as large as they possibly can be to maximize the probability that I can carry out the scattering problem. And in particular, I've chosen them large enough that they enclose an entire, or they cover an entire Cauchy slice in the boundary. If I wanted to go to Poincare, all I would do is I'd remove that identification, and I'd extend the picture infinitely in that direction, and so this R2 region would become arbitrary. Well, it would be infinite, and it would have, in fact, these two disconnected pieces. Is that? Yeah, all of those, well, I cannot put a conical defect in the middle of the space, but all of the discussion that I've been having is, or it's actually Alex's discussion, but you can carry it out in that configuration as well. Yep. Oop.
The fact that you're taking the output points out to infinity in this limit in the Poincare setting is what's going to allow there to be some non-trivial bulk scattering even when there's no boundary scattering. In the Poincare setting,
I'm letting those points run off to infinity.
yeah, in the Poincare setting, if all of these regions are compact,
Yes.
then bulk scattering always implies boundary scattering.
Okay.
So there's no non-trivial setup in that setting, but because you're setting them off to infinity, you're allowing that to happen.
Okay. Okay, I stand corrected by the source, as it were. Yeah, so there's lots of regions here and pictures. If these ideas are new to you, a simpler way to think of it is just in terms of the points problem that I was talking about earlier, but you can think that the input points are the tips of the decision region here, and the output points are no longer on a constant time slice, but they're arranged in a way so that my total problem gets parameterized by these two variables, theta and x. Here was the setup. We had a conical defect, and I'm going to start by thinking about entanglement entropies for the two decision regions. And so I want to think about RT surfaces in this particular picture. And so here are the RT surfaces that we're going to think about. This is the disconnected phase, and so I've got the two associated with C1 and C2. There are two connected phases that I'm drawing here. This surface is common to both, but the second surface in this case encloses the defect. In this case, it avoids the defect. And so these are two distinct connected phases, and we're going to give them some names, in particular D for disconnected. Over here, we're calling it O because the defect punches a hole in the middle of the entanglement wedge, and U, well, the U is, my grad student decided that it is shaped like a U, and I'm not going to argue with her. And so having a connected entanglement wedge, and I'm just going to write things like this, that the minimum of O or U, one of these connected phases, is less than the area of the disconnected phase. One thing is that I've thrown away certain possibilities. These are also extremal surfaces, configurations that I could consider. But I know, for example, in this case, that the disconnected phase on the previous transparency is always going to be less than this phase because this is now extending around the defect, whereas the shorter side is over here. Similarly, with the restriction that theta is less than pi, this, which is also looking more like a U, but this U prime phase is always larger than the O phase, again, because I can find a shorter geodesic over here connecting those two. So we don't have to consider all of the extremal surfaces, but these are the configurations that are going to play a role and can provide or tell us what the entanglement entropy is. So let's compare the disconnected phase with the U phase. And so you'll get a picture that looks something like this. When we're in the bottom, this white region, then X is actually greater than theta. In that case, the two regions are overlapping and we're not interested. In the upper half here, then the two regions are disconnected. And in the red region, that's where the disconnected phase dominates, and the blue region is where the connected phase or the U phase dominates. And that's what that says. And so just to get some context, I picked some particular negative value of M here, and I got this particular boundary. If I change M, that boundary moves around a little bit according to some formula that you'll see in a little while. But if I go to the limit of M equals -1, i.e. the ADS space, then that boundary would take the shape of that dashed line here. I've also introduced the theta plus x line, that diagonal running down the middle here, and I'll explain in a few moments why that line is important in my picture. I can do the same thing for the O phase, the one where the connected, where the entanglement wedge enclosed the defect. In that case, I get a picture that looks like this, and you can see that they're different surfaces and they look slightly different. The key thing is that the O and the U are going to be equal when along this dashed line here. And that's simply because I'm at theta plus x equals pi, so the endpoints of this boundary are precisely pi or antipodal on the boundary. And so in the U phase, I've got an extremal surface that goes around to the right of the defect. The O goes to the left, but they're precisely reflections of one another around the vertical through the middle of the diagram. And so the two entanglement entropies are identical at that particular point. And that lets us then choose which of these connected phases is actually the dominant phase in making this phase diagram. And we choose when I'm above the O phase and below it's the U phase. And so this is the phase diagram for the entanglement region of my two input regions. The disconnected again dominates in the red region, but I've got a connected phase everywhere where there's blue. And so holographic scattering is possible. On the other hand, we have to ask the question, when do we actually get holographic scattering? And there what I want to do is I want to know that I can get, a scattering process. Oh dear. A scattering process that starts in these two regions, in the input regions and makes it out into the output regions. At the end of the day, that amounts to finding a null geodesic from the disconnected or the geodesic defining the entanglement wedge for those two to a common point on the entanglement wedge between the two outputs. And one can go through calculation and one finds a picture like this, so that in this region up here, even though I've got a connected entanglement wedge, there is no scattering. There's only scattering in the remaining blue regions here. And that boundary that is defined here is given by some formula like that. But it turns out that that boundary is precisely the same boundary we found when we were comparing the disconnected phase with the U phase. You can see that the picture that we have, or the two pictures, look somewhat similar, that there's just this region near the theta equals x line that contributes. And so what that's saying is then that in the regime where we have U less than D, that's definitely a part of where I've got the connected phase, but when U is less than D, that's precisely when I get holographic scattering. And so it's really this U phase that tells us about holographic scattering, even up here, where the entanglement entropy is really given, though, by another set of extremal surfaces. And so this is telling us something about holographic scattering, but it really isn't the minimal RT surface in that particular regime in the top half or in the dark blue region. I can tell a similar story about black holes, but I don't have enough time today. But I'll just say make some brief comments. I have very similar entanglement wedges that I'm concerned with. There's a D, an O, and a so-called U region. The one difference now is that I've got a black hole horizon in the middle of the space, and so this homology constraint means that I have to take that into account when I'm calculating entanglement region or entanglement entropies for the O region. There's a complicated story well, it's not that complicated. There's a very similar story. You end up with pictures like this. And at the end of the day, it's really the U or the U prime. It turns out that theta above pi is now a distinct phase. It's really those two that control whether or not there's holographic scattering, even though in some of these regions, it's really the O that is telling us about the entanglement entropy. And so what we found is that it's really, well, there is a connection between holographic scattering and some set of non-minimal RT surfaces. And so let's think about those and what is this really trying to tell us? As it said here, or as I've emphasized, this is really a stronger statement than just saying that I have a connected entanglement wedge. And our supposition is, or our hypothesis is that this is telling us that the entanglement isn't just entanglement that's giving me a large number of correlations, but that I actually have to organize the entanglement in amongst the matrix degrees of freedom in a very specific way. And some evidence of that comes from the idea of entwinement that was introduced by some of the audience here. I know Jan is over there, oh, there he is up in the back. Bartek, so we've got at least two of the co-authors. And what they were doing was precisely thinking about non-extremal surfaces and what the behavior or what the entanglement or what the implications of those might be for sub-ADS scale physics in the bulk geometry. So let's think about a conical defect where I choose a very specific value for the mass parameter. And in general, it can be -1 over some integer squared. In the picture, I'm thinking of -1 over 9. It turns out that in this case, the conical defect is just a Zn orbifold of the ADS space. I've actually cut out a huge portion of the ADS space to make the conical defect, but it's a very specific fraction of 2 pi, and so I can think of it as an orbifold. So here I've got, well, that alpha would be 2 pi over 3, and it would actually be, well, I could paste 3 of those together to make a full ADS space, and so here I've just got ADS space. And what I can do is I can think that the physics here is equivalent to the physics here as long as I make certain restrictions. So for example, the Newton's constant in this theory must be larger than I started with, and similarly the number of degrees of freedom, or the C that characterizes the number of degrees of freedom, has been divided by n. And so essentially what I've done is I've taken some of these internal degrees of freedom and I've distributed them, or I've spatially organized them in the covering space here. And so if I go back and I think about entanglement entropy, Now the regions that I chose in my original conical defect become a collection of regions distributed around the ADS space. And so in the case where I'm asking, is there a large mutual information between these original regions, that amounts to saying, is there a large mutual information between these distributed regions in the covering space? And so the pictures that I've shown you before may take forms like this. This is the O geometry, or the O phase, where in fact it encloses the center of the space, which is where the conical defect would have been. And then here are various U phases. In fact, they involve various disconnected components. So there's a symmetry here, but there's one entanglement wedge. Here there's the symmetry, but in fact I have 3 entanglement wedges. And so, as well as thinking in the covering space, as well as thinking about these distributed regions that correspond to what I had in the original space, I can think about the individual regions which make up those, and I can think about the entanglement entropy of those individual regions. And what we're saying then is that U less than D is saying that there is a lot of mutual information between this V1 and V2 within one single pi region, or the U prime is saying there's a lot of mutual information, a lot of correlations between this and its, well, the next one over in the next pi region, like that. And so what this is saying, or what this is suggesting, is that, again, the entanglement entropy isn't distributed in some way that mixes all of the regions together, but the entanglement is arranged in a very particular way in the covering space that's connecting neighboring regions. And you can come to a very similar conclusion if you think about ungauging, or you think about entwinement in more general geometries. For instance, a black hole, you can think about a covering space, a threefold covering space for your favorite BTZ black hole. And so, sorry. That really brings me to the end of the talk. The key idea is, well, one idea is holographic scattering is a very interesting idea, and the relationship to entanglement. What we've shown with some simple examples is that having a large number of correlations is good, but that entanglement actually has to be arranged in a very particular way. And so there are lots of questions here about how one might delve into that more deeply, but I'll just say there are lots of questions to explore, and thank you for your time.
Okay, we have plenty of time for questions. And Jonathan?
Great, thanks, Rob.
Yeah.
So it's my understanding that what you said was there are, in this conical defect example, there are settings where you have large correlations but no scattering, and these are exactly the settings when the O-type region dominates over the disconnected phase, but the U-type region does not. The O-type region dominates over the disconnected phase, so you still have large correlations?
D would not dominate.
Right.
Yeah.
Do you ever have settings where the U-type region dominates over the disconnected phase, but the O-type region does not? What I'm trying to get at is that I'm trying to understand why the dominance of the U-type region is important, as opposed to just saying, you know, is it maybe just the case that we need all of the candidate connected phases to dominate over the disconnected phase in order for scattering to be possible? I'm having trouble understanding why U is special.
I see. I was going to say in the bottom half of the diagram, but I don't know, but I think you're right, that anywhere that U is dominating in my examples, the O would also dominate over the disconnected phase. Or, no, that's not, there's a thin, yeah, no, there's a thin wedge where that doesn't happen, but yeah.
Sorry, maybe Ronak.
Okay. Can you go back to the slide where you showed the U-type diagram in the ungauged Zn unfolded geometry?
I can try. Is this?
Yes. So the U-type diagram is the one where it looks like the different copies aren't entangled with each other. Is that right? So are you saying that the thing that you need is that the sort of like different copies or different parts of the internal degrees of freedom aren't entangled with each other?
I'm up to the fact, in my example, that's true, up to the fact that here I divided things up in a particular way that this was 1 copy, 2 copies, 3 copies. Here, I'm stretching across that boundary, but that's really nothing to worry about. It's just 2 distinct regions are being entangled. But in those examples, yeah, they're not entangled.
Sorry, didn't you say that the U prime region never dominates? I thought the U was what was important.
Yes, I did. In the example, you can run into, I'm not sure that I'm going to be able to do it for you right now, but if you change the examples or if I just think about a broader set of regions, and you allow the angles to move around a bit more, then U prime would be playing a role. I mean, for example, so I restricted theta to be 0 to pi, but if I go over here, then it's U prime is really playing the role of U. So this was, yeah, there's a more general discussion.
So you're saying you have at least 2 different ways in which internal degrees of freedom can be entangled, and there is still holographic scattering.
Yeah, and in general, I drew a picture like this over here, where you sort of see entanglement between either 2 neighbors, because you can have, again, in a more general context, you can have situations where, well, if I examine these 2 neighbors, I see large mutual information. If I examine the next 2 pair of neighbors, there's also large mutual information. It's not one or the other. In general, you can have both.
Okay, thank you.
Hey, can I?
Oh, sure.
I have a quick question about the interpretation of this connecting causality in the bulk to the saddle point that dominates, RT. So we think of even when you're disconnected, we think of the connected saddle as some sort of non-perturbative correction. It's very small, right? Exponentially small correction. Do we think of this as some sort of, are we thinking of like some sort of non-perturbative?
Sorry, can you?
So you have
You're thinking I've got 2 saddles.
They're competing.
Okay.
Right? As n goes to infinity, there's a phase transition.
Okay.
One of them wins.
Yeah.
But when n is large but finite, both of them are present. One of them is exponentially
Okay,
small.
I see. Yeah.
Is the presence of the exponentially small saddle to be interpreted as some sort of violation of causality in the bulk or seeming violation of causality in the bulk? Because these guys would miss if you would not be able to scatter in the bulk. Like you could probably tune the geometric setup, because the reason that they can scatter in the bulk is that you said that there is a connected region in the bulk, right? But let's say we're in a setup where there is no connected region, so they cannot scatter causally in the bulk.
Okay.
But the exponentially suppressed saddle tells you that there is a small amplitude for such a process.
Oh, no, I'm not sure I would interpret it that way, in that what you're saying is, I mean, if we set ours aside, what you're saying is you need a large amount of entanglement. What you're saying is there are situations where I don't have n squared amount of entanglement. I've got order 1 entanglement. And then you're saying there's also, you know, an exponentially suppressed correction to that. So I just don't think, well, right.
I mean, maybe in that configuration, there's just no scatter. So you still get some answer, which is order 1. And in that configuration, there's just no contribution to bulk scattering. And we don't have to have bulk scattering in that contribution, in that configuration.
Hey, Rob, can I ask a question?
Okay, so I have a very generic question. Like, does this theorem shed any light on entanglement or reconstruction? Like you can rewrite your bulk fields in terms of boundary when the edges are connected. Does this theorem shed any light on that or not?
I think the short answer is no, but certainly entanglement wedge reconstruction plays a role in that you're saying, you know, I have this or in these situations, I have a connected wedge, entanglement wedge, which means that, you know, data in the boundary regions, I can reconstruct interesting operators that are deep in the bulk. And so, you know, avoid the causal or the scattering, sorry. So even though scattering isn't obvious in the boundary, you can imagine that given that data, you can reconstruct things in the bulk that are allowing or facilitating this scattering in the bulk.
Maybe last question for Bartek.
Hi, Rob. Do you think this communication task is impossible in non-holographic theories? As in, should we say holography allows us to carry out the task? Or it's more like holography reveals that it's possible to do this task at least in some conformal field theories. But maybe if we had a non-holographic theory, it would also work.
I think it's closer to the second one. What you're learning is that in a quantum system where you can use entanglement as a resource, you can do, well, you knew that anyway. I'm saying it in an obvious way. You can do things that you couldn't have done in a classical setup. I mean, really the key here is that your input regions, as well as, you know, as well as putting whatever signal and message you want in there, there's a lot of quantum correlations between the two that are facilitating something that you couldn't have done without those correlations.
Okay.
So I think the second version of your, I'm clearly too jet lagged, but the second version of your conclusion, I think, is the correct one.
Thank you.
Okay, so maybe let's continue with more questions during coffee break. Let's thank Rob.